I don't know, can I get started or do we need to? Awesome, okay. Yeah, hi everybody, my name is Mark. Glad to be here to tell you a bit more about the kind of work we did on languages for quantum classical programming at Quantinuum. In case you haven't heard of Quantinuum before, do I need to point it this way? No. I'm going to do some technical talking. Quantinuum is a quantum computing company. We're based in lots of different places around the world. In particular, there are some big teams in the US who are mostly working on building actual quantum computers. And then we have a bunch of teams in Europe and Japan, and mostly working on actual applications of quantum computing and also software. And in particular, our team in Cambridge, UK, is working a lot on programming languages and compilers. And that's also the team where I'm based at. So in particular, if you've ever heard of Ticket, the kind of quantum compiler optimizer, that's one of the things we're developing in the office in Cambridge. And while this talk is mostly going to be about software and programming languages, I just want to briefly start off by very briefly talking about actual hardware, because this is sort of informing the way we view high-level abstractions and how we want to program these systems. So it's good to know at least a little bit about hardware as well. So at Quantinuum, we're building ion trap quantum computers based on the QCD architecture. I'll explain what this means in a second. And last year, we released our latest device called Helios with 98 physical qubits. Here you can see an actual picture of our ion trap. I hope you can see 98 blue dots spread around here. And each one of those dots represents 1 qubit in our device. Or to be a bit more precise, each dot is a pair of 2 ions. Right? We have one barium ion, which actually stores the quantum state in its spin. And then we have a second ion that is used for cooling. And yeah, that's what QCD stands for. You have a charged couple cluster device, so 2 ions together that are used to control the system. Okay? And yes.
What does it mean that the ions are used for cooling?
Oh yeah, so the problem is, so these things are suspended in a magnetic field. So you can apply current and you can move them around, or you can hit them with lasers to do stuff to them. The problem is this heats up the system, and if your system gets too hot, then your state coheres faster and you just get noise at the end. So you somehow need some way to cool it down. And the way this works is you have this second ion here, and if you hit this with a laser, you can kind of you can do some interference thing where this thing gets cooled down, like hitting right frequency on the ytterbium ion. So actually, like hitting it with lasers makes the barium ion cooler. It's roughly the idea.
Either way, the whole system, through the coupling, but
yeah,
through interaction with the one that does carry the data.
Yeah, pretty much. Yeah. So the nice thing about ion traps is that these things can move around, right? So it's not like in other architectures like superconducting qubits where your qubits are fixed. Here they can move around. In particular, in our device, we have this big ring thing here, right, where the ions can move around in a cycle. And then there's this X-shaped junction where you can take stuff out of the ring and move it into this zone over here. That's where the actual quantum gates are happening. Right? So you can take an ion, you can rotate it through the ring, take it out, and then at this point, you can zap the laser to do some operations, right? Like measure it, apply some gates, or you can bring 2 ions together and then entangle them by firing a laser edges. Okay? So yes, so that's a picture from that. Not sure well you can see it, but it's basically lots of lasers, and there's like a vacuum chamber. Yeah. So people usually show these like fancy dilution bridges when picturing quantum computers, but I think lasers also look pretty cool. Right? So that's how our lab looks like. Yes. Sorry. It's like some visible, some like infrared. There's a mix there. I think we're also trying to get a bit away from these like very high frequency things because they start damaging stuff. But take it with a grain of salt. I'm not a physicist. I'm not working on these hardware systems. But my understanding is that there's like a mix. So, yeah. One do all of these. One advantage of ion traps, as I said, is that things can move around. So it's very easy to take two ions, arbitrary ions, and then apply gate to them, right? So we have all-to-all connectivity. And again, that's not like other devices where you need to do these weird swaps and routing things to apply arbitrary gates. Also, ion traps are very good to have like low error rates. So our latest device is like the order of 10 to the minus 4 for 2 qubit gates and 10 to the minus 5 for 1 qubit gates. And that's sort of the best state of the art that is currently possible in production devices. Right? One downside of ion traps is, of course, that they're like a lot slower than other architectures because we have to physically actually move stuff around. I think that takes some time. On the other hand, this also gives you the opportunity to do some interesting stuff while things are moving around while you have to wait. For example, you could run some interesting classical computation in the meantime and do some cool stuff with that. Okay? In particular, our latest device comes with a new thing we call real-time engine, which is the capability to like run arbitrary classical logic while you're kind of waiting for other stuff to happen. Right? For example, the way these ions are moved around, or like which ion to pick, where to move it, this computation is happening in real time instead of having to do this ahead of time. Okay, but I'm getting a bit ahead of myself. The main point I want to make here is that there's some interesting opportunity for mixing quantum and classical computation, in particular with these ion trap devices where you have more time available. Yeah, and that's kind of what I want to focus on this talk, namely interesting ways of doing hybrid quantum classical computation, which is something I think you've been covering in this course as well. And particularly focusing on like nice ways to program these systems, like what should a language look like to do these computations. I will need to be a bit careful when talking about this because hybrid quantum classical computation can happen at quite different timescales. Okay? On the one hand, we can have this very large timescale picture. What I'm imagining here is we have a classical computer that maybe produces some circuits, and then you submit these circuits to your quantum processor, the QPU runs it, maybe for many shots, and then reports these results back. And then your classical computer can decide what to do next, maybe make a new circuit, submit it again, rinse and repeat. And maybe you don't just have a single CPU, but maybe like a whole HPC cluster with like CPUs, GPUs, whatever, all distributed. Maybe you even have multiple QPUs that like are networked or whatever. But the main point I want to make here is this classical and quantum domain here is still like fairly separated, right? In particular, there can be an arbitrary time separation between classical and the quantum part here, right? I could say here, suspend in the middle, and then start working like the next day or something. There's no reason why this needs to happen in like a short time or something, right? Maybe you need to talk over the internet to talk to this QPU, for example. Or maybe you're in a queue and need to wait like a week until this is run. Okay, well, it's all fine because the level at which we're talking here is just whole circuit sent over, and then short result comes back and you decide to do something. And that's kind of one way to do quantum classical. An example application of this would be variational algorithms like VQE, where you kind of send a circuit over, and then depending on what results you get back, you update some parameters in your circuit, right? And then you go again, and you kind of repeat until you reach some ground state or something, right? So these are these typical variational algorithms that fit into this large timescale quantum classical thing. However, if we want to peek into this QPU box, we will find that inside our quantum processor, there's actually also some classical interaction going on. Right? So this is a very simplified picture I've drawn here, but we could imagine something like our QPU actually contains a classical coprocessor that talks to the control system. For example, it says, fire this laser now, or apply a current to move this ion around. And there's some like classical logic that's needed to actually make this happen. Okay? And as I said before, this is like an interesting opportunity because this classical computer inside my QPU can also do other interesting stuff. Right? For example, depending on what like individual mid-circuit measurement results I get back, I could dynamically decide what to do next, right? Which has some interesting algorithmic applications that I will get to a bit later. So my plan for this talk is to show you programming languages that attack this problem of large timescale and small time-scale quantum computing from both ends of the spectrum, right? And first, I want to start off with this large time-scale thing, and then in part 2 of the talk, we look at the other side here. Okay. Yeah, as I said, one key thing here is that in this large timescale picture, your classical and quantum parts are very separated, right? They sort of form two distinct worlds. We can kind of think of the quantum worlds, the new worlds, and the old classical worlds. And this distinction not only happens on the linguistic level, but also on the language theory level. I'm sure that maybe you've come across this before. One example of this would be that in our classical world, data is usually copyable and erasable. So I can take some block of memory, I can copy it, I can delete it, that's fine. Whereas in the quantum world, I can't do this, right? Qubits are linear. I can't just clone a state or discard it. Doesn't work. Or if you prefer to think of it more in terms of language semantics, in the classical world, we have like a nice, often Cartesian closed structure, whereas in quantum, everything is like only monoidal, if that means something to you. If not, it's not important. And then what I mentioned before, in the setting here, we can think of classical computation as basically being totally offline. We have an unlimited amount of resources, right? We can spin up a big HPC cluster and let it run for a whole day if we really wanted to. There's no reason why this needs to be bounded. Whereas in the quantum domain, everything is very limited. We need to make decisions very quick. We have very little time. Otherwise, our qubits are going to decohere. And also, we have very few qubits, right? So everything is very restricted, and we need to be very careful to not run out of time or qubits. Yeah, and the one challenge, I guess the thing we've been wondering about is what would be a good language to express this distinction in a nice way, right? So what are kind of type systems and interesting abstractions we can use to make this distinction very clear and reason about it? And this is where our language Brat comes in. One motto for Brat that I like to give is basically us trying to have as much fun as possible with type theory. So this started as a knowledge transfer partnership with Conor McBride from the University of Strathclyde in Glasgow. So he's sort of the academic part of this project. And then he teamed up with my colleague Craig Roy, who worked on the initial kind of development of Brat. And then later on, some more people joined. But basically the pitch is, what are like fun ideas from classical PI theory, which Conor is a big expert in? Can we apply some of that stuff to quantum and build a nice language? Okay, so I put some buzzwords here. It's purely functional, more things, but I will get into detail what those mean later on a bit as well. One last note on the name, in case you're wondering. The name Brat comes from inverting ticket, which is the compiler we've been working on before. So if you take T and cat, you flip it around, you get a bra and a T. So that's where Brat comes from. Right, so I would stress that we've been doing Brat long before it was cool, right? Yeah. Yeah, and one of the key pitches of Brat is that we take this quantum classical distinction really seriously, right? So we want to have a different type discipline in those two worlds, but kind of unify it in the same language. Right, so how does it look like? Here you can see a signature of a function circuit in Brat that takes 2 qubits and returns 2 qubits. Right? So it's basically describing a circuit that acts on 2 qubits. Right? Straightforward, hopefully. And then we can also have classical functions that act on classical types like integers, floating point numbers, and so on. And we distinguish these quantum and classical functions by the arrow symbol. So we have the classical word, we have the normal arrow. Quantum word, we use this lollipop from linear logic. One interesting question we could ask now, though, is what is the type of circuit itself, right? Is circuit a quantum type or a classical type? If we just write this down like this, we could imagine kind of that being that's what the type of circuit is. Right? We want to do functional programming, so we better be able to reason about higher order functions. So we could give circuit this type here. And clearly, this is describing some sort of quantum computation. If I want to run the circuit, I better have a quantum computer to actually execute it on. On the other hand, if I just think about what a circuit is, in a sense, it's just classical data. Right? If I want to, I can I don't know, open my laptop, type up some gates, whatever, without having access to a quantum computer. That's just fine, right? It's just a data structure that I can create, manipulate fully classically. So there's a distinction here between what resources do I need to run the thing versus what do I need to just describe it or have it around as something classical. And in Brat, we want to make this distinction very clear. And that's why instead of giving circuit this type here, I think slightly different, we introduce these braces around it. Okay. What this does is it kind of turns the computation, which is quantum, into what you call in PL theory a thunk. So just the kind of classical description of what to do, and which we denote using these braces. Okay. So in Brat, a circuit is a classical type. However, if you want to call the circuit or run it, that's only possible if you're actually inside the quantum world. Okay, does it make sense so far? Yeah. One of the mantras of Brat is that we have this overall picture of the job of the classical world is to construct a circuit or construct some kind of broken representation that we can then at the end send to the quantum computer. And the important thing is that once we are here in the quantum world, we no longer have to run any classical computation, right? They're fully separated. We're able to evaluate all classical stuff ahead of time. And then what's left is just a circuit structure that we can run. You could also, like one term for this would be stage compilation. So we have these two different stages where you first do all the classical stuff, and then we get like a result back that's purely quantum that we can execute. And to drive this home even more, here you can see the signature of the RZ gate in Brat. So that's the like rotation around the z-axis. And the way this looks like is RZ is a classical function that takes as input a classical floating point number and then returns a classical thunk describing a 1-qubit operation. Right? And Brat's type system guarantees that whatever computation is required to figure out what this rotation angle should be can happen ahead of time classically. Right? So whatever you need to compute this float, it definitely won't depend on information that's only available at runtime in the quantum world. Right? And that's something that kind of this distinction in Brat definitely guarantees. If you're interested in more of the theory behind this, so particularly the theory behind distinguishing between computation types and then classical thunks or like, so okay, the distinction between computation types that are not values and then thunking them to turn them into a value, this is called a call by push value. A lot of the theory behind this has been developed by Paul Levy. And I highly recommend having a look at this because it's quite nice as a kind of model of computation because it unifies call by name and call by value in a fun way. And it's also good for reasoning about side effects. So if you want to learn more about this, I recommend having a look at this 2022 tutorial by Levy. Oh, let me get rid of this. Right. Okay. So that was the quantum classical world thing. Brat has some more fun features. In particular, in the examples I read before, we have this structure here where circuits can take, or functions can take multiple inputs and return multiple things. The way we kind of do this formally is using row typing. So if I have an expression A of type X and an expression B of type Y, then we allow you to write A comma B for the with of type X comma Y. And we call A comma B a row and X comma Y a row type. So the circuit here is a function that takes as input a row of 2 qubits and then returns a row of 2 qubits. Importantly, this is not the same thing as tuples, right? Because in tuples, you can have some nesting structure. I could have a tuple of tuples. I can arbitrarily nest these, whereas rows are just flat. So if I have 3 things, A, B, C, I just write A, B, C. There's no way to put parentheses or like put a grouping in there. In other words, our rows have a monoidal structure, so like fully associative. And we take this one step further. If I have 2 functions, f and g, so from x to u and y to b, then we also allow you to write f comma g which now is a new function that goes from the row xy to the row ub. Right? So in a sense, you can think of this as part of the composition of data, and this as part of the composition of computation. And this syntax is actually very nice for writing quantum circuits. I'll show you an example. So here we could say circuit is just h, s, where h is the 1-qubit Hadamard gate function, and s is the 1-qubit S gate function. And if we draw this as a circuit, we get something like this. Okay, where I took the liberty to draw circuits top down instead of left right. And also notice the braces here again, which lifts this quantum computation into a classical function. Then we can keep playing this game. In particular, the semicolon is the symbol we use to denote composition of functions. So here we can do first h, s, and then we can do cx, which now acts on both qubits. And then, for example, we go and imply t, and this pipe symbol is just our syntactic sugar for an identity function. Right, so with this syntax, we have a very nice way of compositionally writing circuits. Right, so we, unlike other languages where you just have points and you pass them around, here we build circuits purely via composition. So a different way of thinking about this is that this comma is doing a tensor product, and then this is just doing composition of circuits or composition of linear operators. Of course, if you really want to, we also support point style stuff, right? So instead of defining circuit compositionally, you could also define circuit in terms of how it acts on the two input qubits Q1, Q2, and then do some let bindings to just apply the gates, shadow the thing, and then just return the row at the end. Okay, but in many cases,
is there like a type level guarantee that like the gates are all of the same dimension? Like what if I put like a sequence where the first thing is like I put h s and then another s, like what are like telling that that's not right?
Exactly. So the way the type checker works is we maybe I'm taking this. Okay, so I can talk a bit more about the type checker later, but the way it works is we basically have a bunch of inputs that we try to kind of connect up or check in a sense, or synthesize types for, and we try to map them with what the signatures here are. So to answer your question in short, if you do something that doesn't match up with the signature, you will get an error. And then this information flows sort of in both ways.
Yeah, I guess it makes sense. Composition of normal functions, you can't just the output type and the input type next.
Yeah, it's basically that. Yeah. Okay. Yeah. So if, for example, if instead of cx here, I would do a 3-qubit gate, then the signatures wouldn't match up.
Okay.
Or similarly, if I had a third type here, then the cx wouldn't work, but also it wouldn't match the signature everyone's here. So we can steadily guarantee that kind of the step wires up correctly. Yeah. If you're interested in how this is actually implemented, we can talk later as well. But this is the kind of high level thing. I can guarantee you it works. So we can dive into the details later if you want. Yeah. Points as syntax also works, but often this is going to be nicer. If you're interested in seeing if you can push this further, I recommend having a look at this paper by Connor, where they built a type system for MATLAB. They call it LabMate. And the idea is to basically extend this so you not only consider rows, but matrices. So now you can compose stuff horizontally and vertically, right? And then the game is building matrices by kind of composing blocks together in different ways. So this kind of generalizes in a nice way. You could probably also do tensors. Have a look at this paper if you want to learn more. Okay. So we introduced these two words, quantum and classical. How do they differ? Well, one thing is, as I said before, we have linearity. While in the classical world, we can just say, okay, I take an input and I copy it. Quantumly, this is not possible, right? I can't take a qubit and then turn it into 2 qubits. So our type checker is going to say, no, you can't do this. You've already used X, you can't use it twice. And then similar, I can't take as input 2 qubits and I only use one of them. I can't just discard quantum information, whereas classically this is just fine in the quantum world. We also going to get that. one other thing we have in Brat is the concept called money. So far, the only quantum type we've seen is qubit, but we have some more. One of them is money. And money is used to sort of to control how many qubits you can initialize. In a sense, if you want to do a computation and you want to allocate some more ancillas, for example, you have to pay money to get them. And so we have this fresh function, which takes as input one money and then gives you one fresh qubit. And then if you measure the qubit, you get your money back and also the outcome. Okay. What does this give us? Well, similar to qubit, money is a linear type, so you can't duplicate money, right? That's not a thing we're typically allowed to do. The central bank wouldn't be happy if we start printing our own money. And you can't throw it away. I think burning money is also illegal, probably. So the amount of money in qubits stays the same, which means this gives us a nice bound on how many qubits our program is going to consume. For example, if I give you a circuit with this signature, so like a vector of 98 money, and then it returns your money again, you can be very sure, you can be statically sure that your program is going to allocate at most 98 qubits at any given point in time. Okay, so we can statically know, for example, that we could run the circuit on our device because we have exactly 98 qubits, so everything is good. So we will never run into a situation where we run out of qubits because it's nicely bounded by this money quantity. Okay. Yeah. Here you've seen this vector type, which is dependently typed. So it's indexed by the size of the vector. Like here, 98 money, which means Brat has generally dependent types, which come very handy if we're interested in doing stuff like writing algorithms or circuits that are generic over kind of the size or generic how they scale up.
Can you quickly point out what are dependent types?
Yes. So for example, here you see this QFT function takes as input a number. Here this hash symbol is the kind of type level numbers. So it could be like 0 or a successor or something. And then what we return is again a classical func, but now this n, this input value, actually occurs in the type here. Okay, so the return type of this QFT function depends on what value you put in as an input here. And so if I call QFT of 20, I'm going to get back a classical func that is a vector of 20 qubits to vector of 20 qubits. Right? So there's a dependency here. That's what we call it dependent types.
And does that have to be bounded?
It is not bounded, but it is known at compile time. Because so yes. So this n again, QFT here is a classical function, meaning input and output is classical. So n is a value that's known at compile time, which means that we will kind of know what the size is. Yeah.
And it's known as compile time for the Q, like the quantum part, right? Just on the classical part, you would not need to.
So it's a staged compilation picture where you first do type check everything, and then you start running the classical stuff. And then you guarantee that the classical stuff can all be evaluated ahead of time, after which we will definitely know what n is. And then kind of everything and then the stuff we have at the end, so the output that's fed to the quantum computer, at this stage, n will be known. So n will just be a complete number at this point. Yeah.
What's the relationship between this vector type and the row type? We talked about this one.
So good question. The main distinction is that vectors can have a generic size or can have this like n size thing, right? Whereas rows, the size is fixed. So in a sense, if you have a vector, for example, a vector of 3 qubits is isomorphic to a row of 3 qubits, right? That's pretty much the same thing. If you wanted to, you could unpack your vector into 3 wires or into 3 things, and then if you want to, you can also put them back. These are isomorphic. But if you have a vector of length n, where n is something that's kind of not known at type checking time, you can't just turn this into a row, because for rows you need to exactly know the size. Does that distinction make sense? Yeah.
Are these only rows of qubits? You also have money and other items.
Yeah,
they can be
So the only restriction is that you can only have quantum types in your quantum computation. So you can't. So currently we don't allow you to have like floats, stuff like this. Currently the only types we have are qubits. So we have qubits, money, bits, vectors thereof, dependent pairs thereof, and then yeah, I think that should be it. And then in the classical world we have like whatever the usual types you have, and you can't mix the two.
So they can be homogeneous.
Yeah, so the vectors are homogeneous. Yeah, that's all good point. Yeah, that's also a distinction. You can't have a vector with like mixed things in it, which I think you can do with rows. Good point. Yeah. So if you want to implement this QFT function, you do it via pattern matching. So say here the case of QFT0. Now what we have to do is give a function from a vector of 0 qubits to 0 qubits. Well, the only thing that's going to do that is this function here. And we also know that this pattern here is irrefutable. Right? Our type checker knows that the only vector that could be matched against here is the empty one. So that's going to do type check, and we know that this is infallible. And then similarly, if we match against the successor, so this basically means n plus 1, so something is greater than 0, we know that the vector we get in needs to have at least size 1. So there's always a head and a tail. One note here, this comma dash symbol is how we write cons. That's one of Connor's idiosyncrasies, I guess. He doesn't like using like colon or any symmetric symbol for cons, because that apparently throws students up, off if they yeah, because it's not obvious which side is the kind of small and the long end. Right? So we use an asymmetric symbol where the comma means the short bit and the dash is the long tail. Right? Yeah, I'm not giving the implementation here, but you can basically find this using recursion and some helper functions. Right? Very straightforward.
But you still have the double code.
Yeah, I was about to say that.
But I mean, okay.
It's symmetric.
Yeah, it's true. Maybe I need to, yeah, we can debate Connor on that one. Yeah.
I guess they call it like usually like if you don't have cons for the colon for cons, they use colon for type.
Yeah.
But I guess neither of them use colon.
Yeah. I mean, okay, I can get back to Connor and see what he thinks about that, and I can report back what his retort is. Maybe for the types it's more obvious, I don't know. But yeah. He says it's his experience teaching undergrad students, so maybe, yeah. Anyway, that's the decision we went with. Interestingly, so this looks fairly innocent, but the formal theory of trying to combine dependent types with linear logic is not as straightforward, actually. In fact, so the previous attempts to combine Martin-Löf style type theory and Girard linear logic took a while to figure out how to actually do it. So I think the first paper, this is actually also by Connor, the delightfully named I Got Plenty or Nothing, which kind of led to the development of quantitative type theory, which is basically type theory, but you also have linear types. And then, yeah, he and also ASCII kind of figured this out. I'm not going to go into the details because I don't think it's super relevant, but if you want to learn more, you can have a look at this paper. It's basically about when setting up your typing rules, you need to distinguish between using linear stuff, actually using it, consuming it, or just contemplating it. But if you want to learn more, I recommend having a look at this paper. It's, as all of Connor's paper, very entertainingly written. So yeah, have a look if you're interested. Okay, so the QFT example I showed you was pretty basic, but we can do some more fun stuff in Brat. So here's a signature. So this is a classical function where we take a number as input, and then a vector of length 2 to the n, and then we return a vector of length n. Okay, so this is a bit more advanced, but Brat can handle it. For example, if n is 0, then we know, okay, 2 to the n is 1, meaning this must be a vector of length 1. And then we can just, okay, the only thing we can return here is an empty vector. And then if n is the successor of something, so n is equal to n plus 1, then we know that this then this is going to be at least 2 to the n plus 1, okay? And in particular, powers of 2 where n is greater than 0 always have an even size, right? 2, 4, 8, 16. So we have this special vector pattern here, equals ampersand equals, which means split this vector up into 2 equally sized parts. Okay, so this is the first part, and then the second part, these two have the same size. Okay. So in particular, if we match against vectors of n here, then this is going to have length 2 to the n, and this is going to have has length 2 to the m. So together it's 2 to the n plus 1, which kind of matches up with what we want here. In fact, we can do even more, since we know that 2 to the n is always positive. We know that x's and y's also isn't the empty list. So we could even let something like this and say that, okay, we have a first x, then a tail axis, and then y's. And now y's has the same length as these. Kind of thing.
It seems pretty complicated, like type check.
Yes, indeed, indeed. I'll get back to that in a second. Yeah, you can write some expression here. If you want, you can convince yourself that this has length n in total. And indeed, it is not easy to type check, but Brat can do more. In fact, you can leave all of these numbers empty, and Brat will just figure it out by itself. So here, we don't actually have to mention these numbers. And here we can use this nice bang, which tells our type checker, hey, just figure out what this number should be on your own. And then Brat just does it. And the nice thing is that our type checker here is actually complete. So we're not using any kind of weird kind of SMT style solving. We have a complete algorithm that works for our regular numbers, as long as it's only in one variable. That's one important restriction. So we have this fragment of arithmetic, including exponentiation with the successor 0, where we can kind of fully check everything that you throw at it and always produce like a most general solution. This is like non-quantum, not very quantum at all. It just is useful for programming. We just published basically how this checker works at ICFP. So if you want to learn more details how this actually works, everything is in here. But it's basically, you need to, a smart way of dealing with constructors of these different numbers and kind of shuffling back and forth around, and then kind of a smart normalization strategy. So it's on this paper. We can chat later more if you want to go into details. Yes. Oh yeah, it's a pun that becomes clear if you read the paper. Basically, I can probably briefly go into it. So it has to do with how to deal with exponentiation. Is that chalk somewhere? Yeah. So we want think wait, yeah. It's so the central questions we need to be able to answer in order to check these problems is, given any number, is it 0? Is it, let's say, +1? And what is n? Is it 2 times n? And what is this n? And that allows us to kind of check what these constructors mean, right? So for example, here we have a vector of length 1, which means, okay, whatever number is fed in here, it better be a successor. And then we also need to know what this m is. This example here, length 1. So this m is better be 0. So then we can check, is it 0? And then we can infer, okay, n must be 1 in this case. Right. Here we need to check n is better even, since we use this pattern here. So we need to check this. So is it 2 times something? What is this n? then recursively we could check that the head is this, and then basically bubbles all the way through. Okay, so these are the questions we need to be able to answer. So keeping this in mind, we need to design some fragment of numbers where we can answer these questions efficiently. So one, yes.
The exponentiation is limited.
Yeah. So one choice would be our numbers are zero, we have successor of n, we have double of n, and we have, okay, this would be like a natural choice depending on like what these questions are. And we can kind of start asking these questions here. For example, 0 is always 0. Yes. Successor is never 0. Double is 0 if n is 0. And exponentiation is never 0. Right? Or here, 0 is 2 times 0. 0 is so it's okay. Successor is 2 times n if n minus 1. So if n is also a successor, and then n is even. Double things are always even. Exponential things are even unless this is 0. So we can use our 0 check.
Is base 2.
Yeah, base 2. So yeah. So if n is a successor, then this is always even. All good. The problem is this question here. So is it a successor? And successor of what? 0 is not a successor. N is a successor of so suc n is a successor of n. Double is a successor if this is not 0. And then we're here. So the good news is exponentiation is always greater than 0. But what is the predecessor? Right? Turns out describing a predecessor of 2 to the n just using this fragment doesn't work. So this is kind of the roadblock we first run into. Kind of doesn't work. But the solution, turns out, is instead of this as a primitive, we add for full of n, which is 2 to the n minus 1 as a constructor. Okay. And the reason this is called full is because if you think in binary, it's just all ones. And then if you use this as a constructor, it turns out that all of these questions can be answered just using the fragment here. And you can still get 2 to the n, but just plugging a successor onto this. And so we have the same expressivity, but now we can also go arbitrary back from exponentiation. Okay. And then the main question is, how do you actually implement this algorithm here? Turns out you need to be very careful about the order in which you recursively descend this. If you do it wrong, you won't terminate. Yeah. And the reason why it terminates also isn't trivial. I think for details, I will point to the paper. We have a fun category theory proof for why this terminates using pullbacks. So if you're into category theory, you can have a look at this. And there's also a recursive algorithm with like a weird termination measure that you can look at. But yeah, okay. This as an aside, and not really anything to do with quantum, but kind of a fun, nice language to reason about dependent types without actually having to write proofs.
But isn't it like problematic that every number has like multiple representations now?
Every number has multiple representations, correct? But it's not a problem because, well, multiple things. We have a unique normal form, also proved in the paper. So you can always normalize them if you want to.
Okay.
But it turns out you don't have to normalize them. If you just run the algorithm that we come up with, it will work even if you have different representations for the same number. Yeah. It basically, yeah, you need to peel off constructors and then recurse down, and be careful about the order in which you peel constructors off when checking stuff. It's the rough gist.
Just to extend the fragment.
Yeah, yeah. So we don't have a tight complexity bound on it. It's probably, I think it's exponential in the number of folds, I believe. I will need to check the details. I think we don't derive like an explicit bound because the descent algorithm is fairly complicated. But I think it's going to be exponential in how many kind of nested exponentials you have. Hopefully in practice, not too many, but yeah. Okay. Other questions? Otherwise, I will move on from the side. Okay. Of course, dependent types also give us polymorphism. For instance, here dollar is the kind of quantum types. So you can write like a quantum function that takes as input a quantum type. But again, types are also classical data. So X is a quantum type, but X itself is like a classical thing. But similar to how functions are classical, even though they describe something quantum. Same with types here. So classical function. But then here, when we use X, use the lollipop because X comes from the world of quantum types. And then the same story for classical types. Here we have star. That's the kind of classical types. And so these are two generic functions that do identity. That's the only thing they can do for arbitrary input types living in the two worlds. Okay. Points on how it's actually implemented. So we have a bidirectional type checker that's implemented in Haskell. So bidirectional means, sure if you come across this, when we can both check against the type and try to synthesize the type. So if I have an expression, I can ask, does this expression have this type? And then it's either it's happy or not. Okay. Or we can ask, give me a type for this expression. And you can start kind of doing this from both ends, then hopefully infer everything that needs to be inferred. And this gives you kind of a directed way of traversing the abstract syntax tree to figure out types. And then we have an interpreter, also implemented in Haskell, whose job is just to evaluate all the classical stuff, right? So that's this stage compilation thing. All the classical things are evaluated ahead of time, and then what we get out in the end is just going to be this quantum computation thing. And then we have an intermediate representation that is used to describe these quantum things, and that's in Rust. If I have time at the end, I can talk a bit more about what this IR looks like, because it's actually shared between both languages that I'm presenting today. If you actually want to dive in, wait. Okay, let me interpret this first. It's all open source. You can go to GitHub, Quantinuum, Brat, and then check it out. However, fair warning, this is still fairly experimental. Brat is not released yet, meaning there isn't really any documentation, and there's some rough edges, and execution isn't fully worked out yet, right? But you can play around with the type checker. You can also look at examples, and if you're interested in the implementation, and also some weird Haskell hacks that come from Connor's brain, you can have a look. In particular, Connor very much likes to do dependent programming in Haskell, even though Haskell was not designed to do this. But there are certain hacks one can do. So yeah, check it out if you want to learn more. And then there's some kind of other things that Brat has that we can go into if you're interested, but can also move on. It's like we have existential types. So that means return. So okay, are you familiar with existential types before I? Okay, people are. Yeah, okay, then let me quickly say it's I can. So what I showed before is quantification over numbers that occur on the left-hand side of the function, right? So, for example, what can I actually show? For example, here, this says that is a function that works for any number, and I can put in, and any vector I get in, I get a vector out. Right? So it works for all n. In logic, people sometimes say this is like similar to like universal quantifier if you take like the Curry-Howard thing, but that's irrelevant here. But the existential types are kind of the opposite, where variables are not introduced on the left-hand side. For example, here. So let's say I write a foo that takes as input integer, and then okay. So this means you take as input an integer, and then you return a vector of some length, okay, where this length here is, so there exists some length that you return here. So, for example, let's say if, a stupid example is, let's do something first. Okay, so okay, we take n as, let's call this x instead, to not confuse it with this n. Take some number in, we return 1 and then a vector of length 1. Okay, so here we have like some existential thing where the thing that's the type here depends on what we output here instead of what we get in, roughly. So there's only one number we get out instead of working for all numbers. Maybe a bit hand wavy. But yeah, we have something like this in Brat. The syntax is not exactly this, but we can basically return things that aren't quantified at the beginning, but only at the end. We have some syntax for kind of moving wires around. If remember back when I showed you our composition syntax to build circuit with like H, S, semicolon, CX, and so on, this works well if you're interested in building circuits where gates are local. But it gets very like annoying if you want to do a gate between two qubits that are far away. Right? So let's say I want to do a CX between these two guys. In the naive model, you would need to do something like weird something, then do CX, and then you could also like swap it back. Like this, right? This would be very annoying to program. So we also have some syntax to give these things names and then kind of just pull them towards you without having to do the swaps by hand. And then finally, that's something we're currently thinking about that's not implemented yet, is nicer ways to work with vectors. In particular, if you want to index into a vector, say give me qubit at index, I don't know, 5 or something, that's like a principally unsafe thing to do, right? It could go out of bounds, or maybe you even want like a region of things to get out. So what are nice ways to do this in a safe way where it can't go wrong? And one kind of idea from classical dependent type programming are thinnings, which you can think of as masks that tell you which things you want to take out. And then you have like nice dependent type magic to reason about these things and prove things about them. So we have some ideas for how to add this to Brat, however, not implemented yet. So still work in progress. Okay. So, okay, we covered the kind of large timescale thing, and we also dove a bit into the like branching based on control flow, but now we want to like explore this a bit more. So actually, we have to compute in real time while my qubits are. To give you like one example for how this could be useful, here's a circuit that's taken from like this 2014 paper, and what they try to do here is apply a qubit here. For our purpose here, it's not really important to know what this gate does. It's kind of interesting for certain QEC applications. And the task they try to solve is implement this gate using only Cliffords and T gates. And the circuit they come up with or find is this thing here. So we start with our state here, and then we allocate 2 ancillars. We apply a bunch of gates, and then we measure the ancillars. And if both outcomes are 0, then we know we've successfully applied this gate. The bad news is if we get any other outcome, then the circuit will just have done nothing and we get identity. So one kind of trick to fix this would be just keep going and repeat until we get the desired outcome. And then people typically call this repeat and success. And this is an example where you kind of but depending on what outcomes you get at runtime, you need to dynamically decide what happens next. So at compile time, when I'm kind of writing this program, I don't actually know what gates are going to be applied. It really depends on the outcomes we get at runtime. And then it turns out that doing this is a lot more efficient than doing implementations where you kind of try to do something deterministically. So there's an actual benefit you get from using these dynamic schemes. And there are more kind of interesting QC things you can do with this. Like for example, if I try to implement a QC code and I do some measurements and I notice something that went wrong, I need to actually run some classical computation to figure out how to fix it. Then depending on what my decoder tells me, I need to fix up my state. So there's lots of dynamic stuff going on. And then the second argument for why some of this could be good is trying to scale up quantum computation. So here I show you a C-like loop that applies Hadamard gates to like 10,000 qubits. And in the traditional way, we would compile this. What looks at like this. Okay, so like a list of a bazillion gates, kind of Hadamard 10,000 times. And we would take this and then send it over to the quantum computer to execute. As you might be able to imagine, this does not scale well, right? In the future, we're talking millions of gates, millions of qubits, billions of gates. Just unrolling everything and sending the whole sequence of gates over as our representation, that's not going to work. Okay? However, we already have like a very nice and compact way of talking about what this actually is. Okay? So maybe it would be a lot nicer to just send this loop thing over to the quantum device and then just run this loop in real time. And then we don't have to unroll it at compile time. So the picture I showed you before, maybe quantum and classical shouldn't be two separate words, but maybe it should actually be the same thing. Or maybe the quantum device should actually have some more classical. In particular, maybe we should stop talking about quantum circuits and instead talk more about quantum programs. So things with a control flow, or we can run classical logic. Maybe we can even talk to other co-processors. For example, we've been working on calling out to a GPU to do error correction decoding at real time. Or maybe even more crazy stuff like talking to another server on the network while my qubits are coherent. That's crazy, but we've actually demonstrated this. I can tell you more about this later. So there's a lot of classical things we can do. So we want to build a language that does this because our latest device has all of these capabilities. It can do all of these things. Now, what would be a good way to program this? And one of the key requirements here, because it's very different from how people traditionally think about circuits and programming, is to be very easy to learn and use for people. And in particular, for our audience, right? So we're interested to target people like chemists and physicists, people who are not attending seminars on PL theory. So even though it kind of pains my inner functional programming and type theory enthusiast heart, there are going to be some compromise we have to make if we want people to actually adopt this. Okay? So case in point, the Unity Foundation does like a yearly survey where they ask people working in quantum all kinds of questions. And one of them is always, which language do you actually use when you do quantum stuff? Okay? Any of you had a guess what number one could be possibly? Of course, yes. It's Python. Okay, so the reality is, if you want people to actually use it, at least for now, it probably has to be Python. But yeah, that's the situation we're in. So the organization led us to kind of build a second language, which we call Guppy. And the specific goal is to do this quantum classical programming in real time and then make it look like Python. And in fact, it's embedded in Python. And then maybe trick people a bit to do like more safe things than they would do normally in Python. I think the best way to show you this is just run some examples. The nice thing is that since it's Python, it works in the entire Python ecosystem. So this is just like a regular Jupyter notebook. And the way you program Guppy is you just write regular Python functions, except you add this add Guppy annotation thing on top. And this tells our compiler, hey, this function shouldn't be executed by the interpreter, by Python. This is something that we want to compile and run on a quantum computer. And it's, I would say, fairly straightforward. We have this qubit type, and then we can initialize new qubits like this, and then just run and apply gates. Right? Using this imperative syntax here, and then we can also return qubits. thing is that this is embedded in Python. So outside of this function, it's just like normal Python programming. So I can do 1 + 1 here and then get something out. This is all fine. I can also write a second function where I call this valid data, I get out qubits. And then there's one quirk of Guppy is this result function. That's what we use to output stuff. So you can think of it as like a print or a log. You give it a tag name, here Q1, and then we just report measurement results. And then you can see this magic line at the bottom here, what we call compile methods or main. This is what's actually like triggering computation. So I can run this, and if you want to look at what program looks like, we get this enormous thing, which is not nice to look at, and which you also shouldn't look at. That's why I put it away again. Depending on time, I can go with more detail what this is. It's basically our intermediate representation. And Guppy also can expand it with an emulator. So you can just call this emulator thing, and then run this for a bunch of shots, and then you can see, okay, all the answers I get are either 0, 0 or 1, 1, which kind of matches up nicely with the fact that we prepared the valid state here. So that's of course, like if all I want to do is write like a valid state, I don't need a fancy new programming language. That's something I can do in basically any programming language that does quantum, straightforward. The main reason we're developing Guppy is because you want to do these fancy quantum classical things. So here you see again the example from before, where you want to apply this success thing. And with Guppy, we can just write it using normal Python syntax. So we can apply a true loop. We want to apply the gain Q. We allocate 2 oscillators, A, B. We apply a bunch of gates. And then measure both oscillators. If both of them are 0, we succeed. If we log how many attempts it took and we return. Otherwise, we increment counter and then do this start again. I think that's like a very natural way how people would just write this. So hopefully, you teach people how it works because they already know Python. So you can just write syntax as they know it, imperative, and then you get your program out. Okay, so we can run this, and then small experiments. We can allocate qubit, just call this and scan it. For a couple of shots, and then we see on average it takes like 1.6 attempts to succeed. Okay, so that's pretty good. Okay, let's swap back. So how does it work? When I have a Guppy function and I call compile or emulate on it, what's actually happening under the hood? Well, it's essentially the standard compiler pipeline, right? We look up what is the source text of my functions that are annotated. Then I parse them into an abstract syntax tree. I lower into some IR. I also do some type checking. Right? And then maybe I optimize it a bit. We have time to talk about this later. And then I compile it and link it with the runtime. And I get some binary out that I can execute. And importantly, Python does not occur in here. Right? We're not using the Python runtime at all to like execute a program. This binary we get at the end is like fully standalone, completely independent of Python. And that's also, yeah.
Even like a fork.
Correct. So the pipeline is completely independent of the actual Python runtime. And it better be, right? Because we can't, Python is super slow. We couldn't afford to like run Python on a device, right? Our qubits are going to like die because Python decides to do like a garbage collection pause or something. Right? That's not a feasible thing to do. So instead, we just the only thing we get from Python is the syntax, and then everything else is completely custom. And then we get out like a very fast binary at the end. At least that's the goal. Okay, so it looks like, but in principle, if we wanted to, it could behave completely differently. Right? We could make arbitrary choices about what the semantics are. But of course, this would throw people off. If it looks like Python, it should also behave like Python. At least that's what people would expect. So it behaves like Python when possible, right? You can do lots of wacky stuff in Python. It's dynamically typed. You can do very crazy stuff. So we definitely won't be able to support all of it. So it's going to be a subset. But the main thing we want to guarantee is that if our compiler accepts your program, then it's going to act like Python. Okay, so as long as the type checker isn't saying no, you get the semantics you would expect from a normal Python function. Okay, that's the guarantee that we make to not throw people off, because otherwise it would, yeah, people get mad, I think. So this enforces some restrictions. Go back here. First thing, of course, is Guppy is statically typed. As if I define a function that says it returns an integer, but I return a floating point number, Python will be very happy with this, because this is just decorative in Python. But in our language, okay, we actually check this. See, we get, okay, expected int got float. Okay, so that's very standard. Also, I need to identify types. If I just put x here, it says, hey, then I give a type to this argument. Other standard stuff, like I can't add one and none. It's the fairly standard type checking. But there's some more wacky stuff going on as well. For example, here, Python is very happy to accept this function, because Python doesn't require you to actually declare variables. I can just define something and use it, and as long as the current call I'm making actually defines this, it's all fine. Right? So if I call bad with true, it's quite good. If I call bad with false, I get a runtime error. We don't want that. No runtime errors, please. So we also check here, okay, this thing X might be undefined, and we try to be helpful in our error messages. So we tell you, hey, if this B is false, then X is not going to be found. Of course, if I don't use X, then we say, okay, because we try to accept as much as possible. We only say no if there's a very good reason to, either because it's not possible to implement or we have a big performance concern. So here, this is fine again. Something that's also fine is if I this, okay, now it's always fine, that's okay. What's not okay is if I do this. So X is a different type depending on which branch I take. So now it's okay. X could have different types, and either int or float. So say that. And then one other thing I want to mention is that Guppy and regular Python are still distinct. Right? So I think one thing people immediately try to do is something like this, where you define something in Python, and then here, and I try to call Python from it. Try to check this. Python would say no, because it's outside of the Guppy world. Right? We can't just call arbitrary Python because we don't have Python at runtime. Right? We try to compile stuff, so it needs to be the set. Good point. Good point. It could be errors could be better. Indeed. Feel free to make an issue in our repository. Yeah. One thing you can do though is so foo is not available at runtime, however, it is available at compile time. So we have a special feature which we kind of stole from Zig. So if we tag this expression as comp time, then it's fine again, because we tell the compile, okay, I want this call to be executed at compile time. And as long as all the inputs to foo are also on compile time, this is going to be fine. And so if I put a print here, we see that this is actually being executed at compile time. Okay. So X like Python when possible. We're not the only ones trying to do this weird thing of like letting people write Python, but it's actually something else. There's a whole like list of people trying to do the same thing. I would say Guppy is unique in one specific way, namely, it's one thing to like compile Python to something that you can just run and you like link to some simulator, like I showed you in the examples before. It's a very different thing to actually run it on a real device. And as far as I'm aware, none of these existing words actually run on an actual quantum computer. Right? You can simulate it classically, but actually compiling it down to low-level instructions to actually run a device, we're the only ones who can do this. And in particular, in Guppy, there's no change you need to make to your code at all. I can take all the examples I showed you before and just submit them as is and actually run them on our hardware. So that's kind of a thing. But these works are still great. So I think at some point I will also be able to run. For example, if we have kind of more open intermediate representations or people can compile into, at some point it will happen. But I think for now, Guppy is the most advanced one that actually executes. And to give you an example of this, this is my favorite paper I think people have done using Guppy. realization of a quantum streaming algorithm on long-lived qubits. This is a figure from the paper. So what they do here is you have your quantum system and you have a separate classical server. And then your quantum program can actually talk to the server using like remote procedure calls. So the protocol they're implementing is in real time, your quantum device is kind of talking over the Ethernet network to kind of query what the next gate should be. And the cool thing is, all of this protocol could be implemented purely in Guppy. So all the deserializing of RPC messages, controlling it, running the event loop, people just wrote this in like Python syntax in Guppy. Right? And doing this otherwise would have been very difficult because we like hard coded in C and then load it onto the device to do the run experiment. Now everybody can just do this because it's all Guppy. Of course, you need some more work to set up the server, right? But at least the user level programming is very straightforward. Yeah. It's implemented. It is inside Guppy, yeah. So all the kind of classical logic that does this is implemented. Right? So this demonstrates that Guppy is also a capable classical programming language, right? The subset of Python we support is large enough to do interesting classical programming. For example, writing an RPC event loop and like deserializing stuff and so on. Exactly, because it's compiled and so on. Yeah. And then there's a second paper where they use this machinery to improve a protocol to do certified randomness amplification. Maybe I skipped the details because we don't have so much time, but you can use the streaming approach to do interesting stuff. Say, okay. Are we doing with time? 10 minutes. Okay, let's speed up a bit. Guppy can do cool stuff, but great power also gives you like great ability to do wrong things, right? In a circuit, not that much things can go wrong, right? It's a circuit, you can run it. Now we can have lots of new failure modes that can happen, and we want to maybe avoid them. But again, it's a trade-off because, of course, we could just say, okay, we want to do like dependent type theory now, and if you want to index into a vector, just prove that your index is in bounds. All good, okay? But our target audience is not going to be happy with this. So while developing Guppy, we had to follow like a very tight balance of trying to weigh like interesting safety features versus keeping the language usable. However, one thing that we thought is useful enough to force the users is being able to reason about the lifetime of qubits. So this is similar to the discussion we had before about like virtual qubits versus like real qubits and so on. Because if what's actually happening here is in this Guppy snippet, I allocate a qubit. Runtime is assigning a qubit to me, an ion, and then hopefully it makes a smart choice about which one to pick. And then I can apply gates to it and so on. So fine, qubit is alive. However, after measurement, the runtime is going to return this ion and it's not going to be there, right? Qubit is no longer alive. Which means if I want to apply any other gates at this point, our runtime is going to fail and say, no, this qubit has been freed, you can't use it anymore. In fact, it's very similar to classical memory management as well, right? I allocate some memory, I do stuff to it, I free it, and then there's a use after free, which is a big problem in classical programming. And we imagine also going to be a problem in quantum. So we want to do something about it. So yeah, in particular, we want to say this will never happen. We can certainly guarantee that kind of use after free won't be a thing. The main thing in order to, the main challenge in order to guarantee this is how do we reason about a problem like this? So here we call H, and then we call some user-defined function foo. Is the qubit still alive after this point? I mean, it very much depends on what this function foo is doing. So we need to kind of, we need to have a tighter control over at which points in your program you're allowed to deallocate. And any of you heard of Rust before or used it? Yeah. So we're trying to borrow some ideas from there. In particular, we're going to use kind of an ownership concept to restrict who's allowed to deallocate a qubit. In particular, you're only allowed to deallocate a qubit if you own it. So at the beginning, every qubit is owned by the function that allocated it. We can apply gates to it. We can also move qubit into different variables. The qubits are, I can't use qubit. Then we can also return it, which transfers the ownership to whoever calls bar. Then let's see how this plays out in practice. Here's the example I showed you before. We allocate, we predicate. Measurement. And then we try to use the qubit afterwards. Yeah, Q cannot be returned here because we already consumed it at this measurement point. So that's fine. Now, instead, we call it is actually going to compile. And that's because by default, we're going to assume if you write a function that takes in a qubit, this qubit is actually not going to be, there's not going to be any ownership transfer here. So again, taking primarily from Rust, we say that it's borrowed. Right. So here now I can still apply gates to it, but I'm not allowed to deallocate this qubit inside Foo, so we don't have ownership. And similar to Rust, if I now take the second qubit as input here, and here I try to do something bad like this, the pilot wants to catch us, right? You can only ever be one borrow active at the same time. So it says Q has a qubit, you can't borrow it here because you've already borrowed it here. And the nice benefit of this is that we also catch problems like if I twist SCX gate on the same qubit, right? It's all a thing that's physically possible, and a nice side benefit of this is that the compiler also detects this. Okay. Of course, since I don't own the qubit, I can't measure here. So once take ownership of this qubit, and the compiler also tells how to possibly fix it, then we can add this own annotation, which now tells us, okay, foo is a function that actually wants to take ownership of this. And I want to check foo, it's fine. But now we'll check main again. Now main is not happy because now again food is consuming, so I can't return afterwards. So this sort of ensures that the flow of qubits is always kind of maintained, and we already know when something is alive versus when it's not. And then one last thing is if it's just the main function B is the following: it allocates a qubit, it owns this qubit. It applies some gates to it, and then it returns. The problem here is that after leak returns, there's no reference to the separate qubit anymore. It's similar to classical programming. We have a memory leak. We have allocated resource, but we no longer have any references to it. So the compiler is also telling us no here. In other words, if you own a qubit, you not only have the right to measure it, you have to measure it or return the ownership. So this way we try to prevent anonymous. Okay. There's still some compromises, right? Because Rust is quite complicated, and we don't expect people to be able to write Rust in Python. So we have some restrictions, namely borrows are not first class. You can't return the borrowed value, which restricts it a bit. It's more like a calling convention rather than like full references like you have them in Rust, for example. The benefit, though, is that lifetimes are fully automatically inferred. We don't need lifetime annotations, which are like a big pain if you start learning Rust. So we get away with this. Okay. Another problem is indexing into arrays is problematic. So here we borrow, so we got here arrays of qubits, which are like fixed size sequences, and then we can index into them. This is problematic, right? But people still want to index. We have to give indexing to them because they want it so much, our users. But we can't statically check this, right? In general, it's undecidable to evaluate whether two expressions are the same or not. So here we just give up and say, we can't do this. So if you try to do something bad, it will fail at runtime or at compile time. So these are these compromises. Okay, so we have to stop. How is it?